Okay, good morning students. So this is the yesterday continue class Electrostatics Part 7. Okay, so already we know that electric field. What is meant by electric field? It is a region in which electric charges experiences electrical forces. That is called electric field. It is represented by letter E. Electric field is a which quantity? Vector quantity. And also electric field strength. What is meant by electric field strength? Electric field strength at a point in the field is defined as a force acting on a unit positive charge kept at that point. So that is the electric field strength. SI unit of electric field strength Newton per Coulomb. That is the important one. Okay. So in this session we learned about electric field due to a point charge. Electric field due to a point charge. Okay. Electric field due to a point charge. So mention the expression for electric field due to a point charge. Mention the expression for electric field due to a point charge. Okay. So dear students, let us consider a charge, positive charge Q. This is the positive charge. Okay. Around the positive charge, electric field is there. Around the positive charge, electric field is there. What is meant by electric field? It is a region in which electrical charges experiences electrical force, or it is a region or space around the point charge where it influences experience on the other charges. That is called electric field. Okay. This is the positive charge. Around the positive charge, electric field is there. Okay. Suppose, for example, this is the electric field region. Okay. So let us consider just 1 unit of charge placed in that region. Suppose let P be a point at a distance of r from this charge in which electric field will be determined. So let us consider a point P inside the region of electric field at a distance of r from the source charge. This is the source charge, because due to this charge electric field will be developed around it. Okay. So consider a 1 coulomb of charge plus Q. Consider 1 coulomb of charge placed at that point. According to Coulomb's law, some quantity of force acting on the charge. Whenever some quantity of charge, that is 1 unit positive charge placed at that point P, of course, which is inside the field, immediately some quantity of force acting on it. Which force? Repulsive force, because these two are like charges. Okay. The direction of force. What is the direction? Repulsive force. Some quantity of force acting on small q charge like this. This is the repulsive force. Radially outwards. That is the repulsive force. Radially outwards. Okay. In this case, according to Coulomb's law, F is equal to 1 over 4 pi epsilon naught Q and Q divided by distance R square. This is the Coulomb's law formula. So whenever two charges kept in air or vacuum, there exists a force of repulsion between them, because these two are like charges. Okay. So by the definition of electric field intensity, a unit positive charge kept inside the field, some quantity of force will be acting on it. That is called electric field intensity. See, some quantity of charge, small unit charge placed in the region by the definition of by the definition of electric field intensity or electric field strength, some quantity of force will be acting. Some quantity of force will be acting. This is the force. The direction of force radially outwards. So, F is equal to 1 over 4 pi epsilon naught Q by R square. On cross multiplication, like this Q, F by Q. F by Q is equal to 1 by 4 epsilon naught Q by R square. Force per unit charge is nothing but simply electric field strength. This is electric field strength. E. So E is equal to 1 by 4 pi epsilon naught Q by R square. So therefore E is equal to 1 over 4 pi epsilon naught Q by R square. See, dear students, this is the expression for electric field due to a point charge. Electric field due to a point charge. Please one remember it. Electric field depends upon source charge, not test charge. Not a test charge. Electric field depends upon source charge and also depends on distance between source charge and test charge. Source charge and test charge. Source charge and test charge. So, electric field depends upon test charge. Electric field depends upon source charge and the distance between the test charge and the source charge. That is R. That is R. Okay. What is meant by test charge? What is meant by test? This is a test charge. The charge which tests the effect of source charge. The charge which tests the effect of source charge. That is called test charge. Dear students, because of test charge, small electric field also generated around it. But the electric field due to source, the electric field due to test charge does not alter the main electric field. Does not alter the source charge. Does not alter the. So, in the presence of test charge, electric field due to source charge does not alter. That means does not change. Does not change. Okay. Okay, students. This is the electric field due to a point charge. E is equal to 1 over 4 pi epsilon naught Q by R square. Q by R square. So, dear students, see, distance changes, electric field also changes. Distance changes, electric field also changes. See, okay, suppose by using this equation, E is equal to 1 over 4 pi epsilon naught Q by R square. Electric field depends upon source charge and also depends upon distance between the source charge and the test charge. Okay. See, this is the source charge. Let P be a point at a distance of R1 from the source charge, in which electric field will be determined. So, in this case, what is electric field? E1 is equal to 1 over 4 pi epsilon naught Q by R1 square. Similarly, I want electric field at S. What is the distance of S from this charge? R2. Okay, in this case, E2 is equal to 1 over 4 pi epsilon naught Q by R2 square. So, distance changes, electric field also changes. That means, electric field depends upon distance between source charge and test charge. Okay. So, distance increases, electric field strength decreases. Electric field strength decreases. At what point electric field will be 0 due to discharge? At what distance electric field will be 0? that is infinity, because see, substituting in this equation r is equal to infinity, so E is equal to 1 over 4 pi epsilon naught q by infinity square. 1 by infinity is 0. 0 into anything is 0. At infinite distance, electric field is 0. Before infinity, some value will be existed. Some value will be existed. See, dear students, what is the value? So, suppose in this case, substituting r value, any value, some quantity of electric field will be appear. Some quantity of electric field will be appear. So, only at infinite distance, electric field will be 0. Electric field will be 0. Okay. Okay, students. Next one. So, this is the one more bit, very most important. Electric field due to a point charge. E is equal to 1 over 4 pi epsilon naught q by r square. Q by r square. Okay. Okay. In case of positive charge, what is the direction of electric field? What is the direction of electric field? So this is the positive charge. This is the positive charge. In this case, what is the direction of electric field? Radially outwards. Radially outwards, like this. Radially outwards. Radially outwards. In case of this is the magnitude of electric field. What is the direction? What is the direction? In case of positive charge, the direction of electric field is radially outwards. Radially outwards. In case of negative charge, what is the direction of electric field? Radially inwards. Radially inwards, like this. Radially inwards. Radially inwards. This is electric field is a which quantity? Vector quantity. This is the magnitude of electric field due to a point charge, and this is the direction. This is the direction, of course. In case of positive charge, radially, what is the direction of electric field? Radially outwards. Radially outwards. In case of negative charge, radially inwards. Radially inwards. This is the direction of electric field. That is the most important one. Okay. Okay, a small bit. Okay, students. See, F is equal to EQ. F is equal to EQ. R or R. E is equal to F by Q. F by force per unit charge. Okay, students, in vector form, vector E, vector F. Vector E, this is the test charge, represented like Q naught. Represented like Q naught. This is the test charge. Okay. See, what is the direction of electric field and force in case of positive charge? Suppose this is the Q. Around it, electric field will be developed. This is the region of electric field due to this charge, due to source charge. Okay. Let consider a 1 unit positive charge. 1 unit positive charge. Just 1 unit positive, that is 1 coulomb, placed inside the region. Okay. In this case, what is the direction of electric field? Radially outwards. In case of positive charge, radially outwards. Electric field, the direction is like this, radially outwards. And force direction, this is positive, this is also positive. Whenever the positive charge kept inside the field, some quantity of force will be acting on it according to Coulomb's law. What is the direction of force? Both are equal to each other. Direction of force also same direction along the field. In case of positive charge, please remember it. In case of positive charge, the direction of force and direction of electric field both are same. Both are same. repulsive force. Direction of electric field also, in case of positive charge, radially outwards. Radially outwards. Okay. Suppose a negative charge, 1 coulomb of charge placed in the region of electric field. In this region of electric field. In this case, what is the direction of electric field and force? Dear student, this is the positive charge. What is the direction of electric field? Radially outwards. Radially outwards. Okay. This is the direction of electric field. Radially outwards. Force. This is positive charge. What is the direction of force? This is positive charge. This is negative charge. There is attraction. There is attraction between them. Attract towards the charge. So this is the force. This is the force. Positive charge, force outwards. Negative charge, towards the charge. Negative charge, the direction of force is towards the plus Q. Towards the plus Q. Okay. So, dear students, please remember it. The very most important one. Of course, already we know that in case of positive charge, the direction of electric field radially outwards. Radially outwards. Okay. Okay. Next. What is the direction of force? Whenever the positive charge, 1 unit positive charge kept inside the field, and what is the direction of force? Whenever 1 unit negative charge kept inside the field. Suppose 1 coulomb of charge, just 1 coulomb or 1 unit of charge placed in this region, there exists a repulsive force, direction of force along the field. And a negative charge placed in that region, what is the direction of force? Opposite to the field. This is the field, positive charge, radially outwards. So, 1 unit charge or 1 coulomb charge placed in this region, what is the direction of force? These two are attracted. So, attractive force like this, attraction, that is towards the plus Q charge. Direction of force towards the source charge. Okay. In this case, negative charge case, electric field and force are opposite. Positive charge case, electric field and force are same. Electric field and force are same. Okay, students, this is the important one. Please remember it. Please remember it. Okay. Next one. Next one. Superposition principle. State superposition. State superposition principle for electric fields. Electric fields. State superposition principle for electric fields. Superposition principle, already we know that. Superposition in case of forces, already we know that. Same manner, this is the superposition principle for electric fields. Dear students, suppose consider a number of charges. Of course, consider a point P. This is the point P. Consider a charge Q1 at a distance R1 from the point P. From the point P. Similarly, consider another charge. Consider another charge Q2 at a distance R2 from that charge P. Sorry, from the point P. Of course, consider number of charges Q3, Q3, Q4, Q5, and so on Qn. Okay. Because of charge Q1, electric field will be produced at P. Similarly, because of Q2, electric field also produced at P. Of course, these two are positive charges. I will take positive charges. Okay. See, dear students, because of positive charge Q1, electric field will be produced at P. What is the direction of electric field? Like this. E1. E1. What is the value of E1? Due to this charge. E1 equal to 1 over 4 pi epsilon naught Q1 by, what is the distance? R1 square. Similarly, due to Q2 charge, electric field also produced at P. What is the direction of electric field at P? That is positive charge radially outwards, like this. This is U2. What is the value of U2? U2 is equal to 1 over 4 pi epsilon naught Q2 by R2 square. Q2 by R2 square. R2 square. Okay. The resultant, like this. This is the resultant field. This is the resultant field by the addition of parallelogram law of vector addition or polygon law of vector addition. Okay. See, dear student, state superposition principle for electric fields. Statement. The total electric field at a point due to all charges. The total electric field at a point due to all charges is equal to the vector sum of the all electric fields due to all charges. Due to all charges. Dear students, total electric field E is equal to, or vector E is equal to E1 plus E2 plus E3 plus E4 plus and so on En. Dear students, I am considering only two charges. Okay. So vector addition. Okay, students. Once again, I will repeat. Superposition principle for electric fields. Statement. It states that total electric field at a point due to all charges is equal to the vector sum of the all electric fields due to all charges. That is the statement, simple statement. Okay. So E is equal to, what is the value of E1? 1 over 4 pi epsilon naught Q1 by R1 square. Similarly, E2, 1 by 4 epsilon naught Q2 by R2 square plus and so on plus. What is the value of E1? 1 over 4 pi epsilon naught Qn by Rn square. Okay. So in this, which term is common? 1 over 4 pi epsilon naught is common. So E is equal to 1 over 4 pi epsilon naught is common factor. Q1 by R1 square, Q2 by R2 square plus and so on plus Qn by Rn square. Q1 by R1 square plus Q2 by R2 square plus and so on plus Qn by Rn square. Okay, simply E is equal to 1 over 4 pi epsilon naught. I will take sigma I is equal to 1 to n Qi by Ri square. Sigma means summation. So I value starts from 1 to n. Okay, students, this is the total formation, total electric field due to all charges. So simply superposition principle for fields. It states that net electric field at P due to all charges is equal to the vector sum of the all electric fields due to all charges. Okay. This is the principle, superposition principle for electric fields. Okay, students. Next one. Electric dipole. Okay. Electric dipole. This is the important one, students. What is meant by electric dipole? Two equal and opposite charges separated by a small distance is called electric dipole. See, to equal and opposite charge. This is minus q charge and this is plus q charge. To equal and opposite charges separated by a small distance. I will take d, small distance, d. This is called electric dipole, like this. This is the dipole. To equal and opposite charges separated by a small distance. Equal and opposite charges separated by a small distance is called electric dipole. It's called electric dipole. Example for dipole: molecule, water molecule, molecules of water, molecule of water. So in case of water, one positive charge and one negative charge is there. Molecule. In case of molecule, let us consider molecule. Positive charge and negative charge get separated. Of course, positive charge means protons, negative charge means electrons. So molecule, this is the molecule, negative charge and positive charge get separated like this. This is the example for electric dipole. To equal and opposite charges separated by a small distance is called electric dipole. Okay. Okay, students. Okay, generally molecules are two types. Molecules are two types. Molecules are two types. Two types, like this. Polar molecules, polar molecules and non-polar molecules. Polar molecules and non-polar molecules. So what are polar molecules? In case of polar molecules, the center of positive charge and center of negative charge get separated. It possesses permanent dipole moment. Permanent dipole moment. So what is meant by dipole moment? Just I will explain later. Polar molecules. In case of polar molecules, the center of positive charge and center of negative charge get separated like this. Get separated. It possesses permanent dipole moment. That means it conducts fewer electricity. Okay, example for polar molecules. Molecules of water, molecules of water, ammonia, HCl, HIE, HCl, HIE, so like this, CO. So polar molecules, in case of polar molecules, the center of positive charge and center of negative charge get separated. It possesses permanent dipole moment. Example for polar molecules: molecules of water, ammonia, HCl, HIE, CO. Non-polar molecules. What are non-polar molecules? In case of non-polar molecules, the center of positive charge and center of negative charge coincide. Like this, coincide. Dipole moment will be zero. It does not conduct electricity. Separated means one positive wave or negative wave. It conducts electricity. These are mixed. It is not possible. Electricity does not pass through it. Non-polar molecules, because of the center of positive, center of negative charge coincide. Okay, coincide. These non-polar molecules kept inside the external electric field. The center of positive charge and center of negative charge get separated. However, dipole moment is temporary, not permanent. The non-polar molecules, in case of non-polar molecules, the center of positive charge, center of negative charge coincide. It does not possess permanent dipole moment. Suppose these non-polar molecules are kept inside the external electric field are kept inside the field, electric field, the center of positive charge, center of negative charge get separated. It possesses a dipole moment, but it is a temporary dipole moment. Example for non-polar molecules. Example H2, N2, O2, CO2, like this. These are the example for non-polar molecules. Okay, students? Okay? What is meant by electric dipole? To equal and opposite charges. This is the very most important bit. Another one, very most important bit, net charge on the dipole. Net charge, total charge on the dipole is what? 0. Because minus q plus q, minus 1 plus 1, that is equal to 0. Net charge on the dipole. Net charge on the dipole. Net charge on the dipole is 0. Very most important, students. But electric field, total electric field not equal to 0. Electric field produced due to negative charge, and also electric field produced due to positive charge. Total electric field not equal to 0. But total charge on the dipole is 0. Okay. Next. Electric dipole moment. Electric dipole moment. Represented by letter P. Very most important, students. Electric dipole moment. This is the dipole. Like this. Two equal opposite charges separated by a small distance is called dipole. Okay. Electric dipole moment. So electric dipole moment means, of course, electric dipole moment is which quantity? Vector quantity. Electric dipole moment is defined as the product of either of charge into separation between the two charges. This is the electric dipole moment. Q into D. The product of either of charge and separation between the two charges. Either of charge and separation between the two charges is called dipole moment. In SI system, SI unit of dipole moment, charge, coulomb, distance, meter. Dear students, please remember it. Coulomb meter, not centimeter. Just small hyphen is there. This is a small hyphen. Coulomb meter. Very most important. So this is the magnitude of dipole moment. What is the direction? What is the direction of dipole moment? Conventionally, the direction of electric dipole moment is from negative charge to positive charge. Like this. This is the direction of dipole moment. Direction of dipole moment from negative charge to positive charge. That is the very most important. Please remember it. This is the magnitude of dipole moment, and this is the direction from negative charge to positive charge. Negative charge to positive charge. That is the important one. Okay. So in another way, suppose this is the dipole minus q plus q separated by distance 2a. Instead of d, I will take 2a. Of course, this is the center point of dipole. This is A, this is also A. Okay. In this case, what is the dipole moment? Dipole moment P is equal to product of either of charge and separation between the two charges. 2A, like this. 2AQ. This is also dipole moment. In SI system, SI unit, coulomb meter. Charge, coulomb. This is the distance between two charges, that is meter. Coulomb meter. Okay. Next, please remember it, very most important, dipole moment. Product of either of charge and separation between the two charges. Okay. So next one. Axial line and equatorial line of the dipole. Axial line axial line of the electric dipole. Axial line. See, dear students, this is the electric dipole separated by distance 2a, of course, 2a. Axial line means the line joining the two charges extended on both sides. That is called axial line. Axial line means the line joining the two charges extended both sides is called axial line. Like this is the axial line. See, axial line, very most important, axial line. Axial line means axial line of the dipole. Electric dipole means the line joining the two charges extended on both sides. This is axial line. This is axial line. The center point between two charges, O, the center point between two charges, that is O, is called midpoint of the dipole. This is the midpoint of the dipole. Midpoint of the dipole. Midpoint of the dipole. This is what? This is what? Axial line of the dipole. The line joining the two charges extended on both sides is called axial line of the dipole. Very most important. Okay, students, this is a axial line. Axial line. Next, equatorial line. Equatorial line. Equatorial line of the electric dipole. This is also very most important. Equatorial line of the dipole. So dear students, equatorial line means, of course, see, this is the dipole. This is the midpoint. Midpoint of the dipole. O will be the midpoint of the dipole. Equatorial line means, see dear student, this is what? Axial line. This is what? Axial line. Okay. Equatorial line means the line passing through the center of the dipole and perpendicular to the axial line is called equatorial line. Like this, the line passing through the center of the dipole. This is the center. The line passing through the center of the dipole and perpendicular to the axial line is called equatorial line. Dear student, this is the equatorial line. Very most important. Equatorial line. Equatorial line. Equatorial line of the dipole. See, the line passing through the center of the dipole and perpendicular to the axial line. Perpendicular to the axial line is called equatorial line of the dipole. Okay, these are the two very most important students. Okay, this is axial line and this is equatorial line. This is equatorial line. Okay, students, thank you.